Welcome back, everyone. Electric power networks are undergoing a structural change that is reshaping how energy moves across entire continents. For more than a century, most grids were built around short distances and alternating current, with generation located close to cities and industry. That assumption is no longer holding. Large energy sources are now placed far from demand centers, including offshore regions, deserts, mountains, and remote plains. At the same time, electricity demand is becoming more uneven across regions and across time. Long-distance transmission has shifted from a secondary concern into a central constraint. High-voltage direct current transmission, often abbreviated as HVDC, is already operational on several corridors and planned for many more. These systems are designed specifically to move large amounts of power over thousands of kilometers, with lower losses and higher control. The topic of this video is how long-distance HVDC lines are beginning to redraw continental power maps and change how grids are planned. The traditional grid model relied on alternating current because it was easy to transform voltages using early electrical equipment. That design choice shaped everything that followed. Alternating current works well for regional networks but becomes inefficient and unstable over very long distances. Power losses increase, synchronization becomes fragile, and control options remain limited. HVDC systems were proposed decades ago, but their supporting technology was immature. Today, that situation has changed. Power electronics, insulation materials, and digital control systems have reached a level where direct current transmission is practical at continental scale. Some HVDC links are already operational, while many others are under construction or in advanced planning stages. These lines do not replace existing grids. Instead, they overlay them, acting as high-capacity arteries that move energy between distant regions. We will examine how these systems are built, controlled, and integrated into modern grids. High-voltage direct current transmission operates by converting alternating current into direct current at a sending station, moving it along a dedicated line and converting it back at the receiving end. This basic structure is already operational on several major links. The critical difference lies in control. Direct current allows operators to set exact power flow levels independent of surrounding grid conditions. Siemens Energy Berlin has delivered converter systems that regulate voltage and current with millisecond precision, allowing HVDC links to stabilize surrounding networks rather than disrupt them. These systems are used to move bulk power from distant generation sites into dense load centers. Unlike traditional lines, HVDC corridors do not require synchronized grids on both ends. This allows connections between regions that previously could not exchange large amounts of power reliably. The result is a new layer of grid infrastructure that behaves more like a controllable pipeline than a passive wire. Please subscribe. As HVDC networks expand, their physical scale becomes immediately apparent. These lines operate at extremely high voltages, often exceeding hundreds of kilovolts, which allows large power transfers with lower current and reduced resistive losses. Over long distances, this efficiency difference becomes decisive. Fewer conductors are required, tower spacing increases, and underground or subsea routing becomes practical. Many modern projects use subsea cables to connect offshore generation directly to inland grids. Others cross deserts or sparsely populated regions where alternating current would suffer unacceptable losses. The transmission path itself becomes a strategic asset. Instead of many small lines weaving across regions, planners focus on a few high-capacity corridors. This changes how grid expansion is visualized. Maps that once showed dense local meshes now highlight long straight HVDC routes linking distant nodes. Converter stations are the technical heart of every HVDC link. These installations handle the transformation between alternating and direct current while maintaining precise control. Hitachi Energy Zurich develops converter platforms that use modular power electronics stacked into valve halls the size of industrial buildings. Each module switches thousands of times per second, shaping current flow with high accuracy. These stations also provide voltage support and fault isolation for connected grids. When disturbances occur, HVDC links can reduce or redirect power almost instantly. This capability allows grids to absorb fluctuations that would otherwise cause instability. Converter stations are already operational in several regions and are planned as anchor points for future corridors. Their placement often determines where new industrial growth and data infrastructure will concentrate. The strategic impact of HVDC becomes clear when examining regional imbalance. Energy production and energy consumption rarely align geographically. Some regions generate surplus power during long periods, while others face persistent shortages. Traditional grids struggled to balance this mismatch over large distances. HVDC corridors change that equation. They allow planners to treat entire continents as interconnected systems rather than isolated zones. Power can be routed dynamically based on demand, availability, and network conditions. This does not eliminate the need for local generation, but it reduces vulnerability. Regions connected by HVDC gain access to a wider pool of resources. Over time, this influences where new factories, processing centers, and infrastructure clusters are built. Grid operators are adjusting their planning models to account for these new capabilities. RTE Paris operates high-capacity transmission networks that already integrate direct current links into national and cross-border planning. These links act as controllable gateways rather than passive connections. Operators schedule power flows based on system needs rather than fixed physical constraints. This approach allows maintenance, outages, and demand spikes to be managed with greater predictability. HVDC also supports gradual grid expansion. New corridors can be added without reworking entire regional networks. As a result, long-term planning horizons are shifting from decades to continuous incremental upgrades. The grid becomes an adaptive system rather than a static structure. One of the less visible effects of HVDC expansion is its influence on system resilience. Direct current links can isolate disturbances and prevent cascading failures. Because power flow is actively controlled, faults do not automatically propagate across regions. This changes how engineers think about grid protection. Instead of relying solely on passive safeguards, they deploy active control strategies. HVDC systems also simplify cross-regional cooperation. Different grid standards and operating practices can coexist when connected through controlled interfaces. This flexibility encourages broader interconnection without forcing full harmonization. Over time, this leads to denser continental networks that remain stable under a wider range of conditions. Large-scale deployment requires coordination between transmission owners and technology providers. National Grid, London manages networks that increasingly rely on direct current links to balance distant regions and offshore resources. These systems are operational today and form the backbone of future expansion plans. Tokyo Electric Power Company operates HVDC connections that support long-distance transfers across challenging geography. Each organization adapts the same core technology to local conditions, terrain, and demand patterns. The result is a diverse but interoperable set of corridors. These projects demonstrate that HVDC is no longer experimental. It is a mature infrastructure tool shaping how energy moves across continents. As HVDC corridors continue to expand, continental power maps are being redrawn in fundamental ways. Energy no longer flows only from local sources outward. It moves along planned pathways that connect distant regions into coherent systems. This shift affects investment, industrial placement, and long-term grid strategy. Transmission becomes an active planning instrument rather than a constraint. The growth of HVDC does not replace existing grids, but transforms how they are used. Over the coming years, these corridors will define new centers of reliability and flexibility. They will determine which regions can grow without hitting energy limits and which remain constrained by distance. Thank you very much for watching. Please like and subscribe.